In this lecture, we're going to be reviewing halogenation of alkanes and learning a new method for a reaction called allylic bromination. So let's start out with just a quick review. This is something that we learned at the end of Unit 1, and that was where you could take an alkane and you could treat it with either chlorine or bromine, and you could do light or heat, and then you could put a halogen, a monohalogenation, on the alkane, so it'd be alkane X. And let's go ahead and let's just do an example. So let's say we had something like that, and we treated it with Br2 and light, and we could put a monohalogen onto the alkane. And we saw that with chlorination that there was a complication, and that was that chlorination was less selective than bromination. And we actually did some calculations with that, in that you tended to get a large mixture of products. So let's say we had something, let's do a pretty straightforward one, maybe straightforward, like this. And if we had Cl2 and light, chlorine wasn't tremendously selective, more so for one position than the other. It preferred tertiary by a little, but secondary was still pretty good. Primary wasn't terrible. So you were going to end up with chlorine at the primary, and then you'd have a chlorine at the tertiary, and then chlorines all along these secondary positions. So chlorine there, and then I think the last different one would be out there. So you would end up with pretty decent amounts of 5 different products. So doing a chlorination of an alkane was not a particularly effective method of putting halogen on, because you'd have a big separation step. Conversely, if you did bromination of the same molecule, Br2 and light, bromination really favored the tertiary. If you remember the ratios, it was like 1600 was the tertiary rate, and it was like I think it was 87 was the secondary, and 1 was the primary. So bromination wildly favors the more substituted positions. Chlorination, it was 1 to about 4.5 to about 5.5, not much of a difference. You could see huge difference in bromination. And so if we did Br2 and light, I've got a tertiary position that is right here. And so I know that if I do this bromination, tertiary is wildly favored, that I'm going to get right there plus minor, and we're talking minor, bromination at other positions. Not really enough to worry about, right? With a 1600 to 1 ratio, I'm going to get tertiary. And so when you're doing a halogenation of an alkane, do bromination. Practically no one does chlorination because it's much more predictable when you brominate. Your yields are going to be better for the most substituted position, and I'm not going to have just a bunch of separation steps. Okay, so let's just do a practice one. Let's say I had something like this, and I did Br2 and light, and I asked you for the major product. Well, you find your most substituted carbon, which is that tertiary one, and you put a bromine right there. And that is the major product of bromination. Chlorination, It's a whole different deal. You'd have multiple products, you'd have to do the calculation, there'd be mixtures. Just don't chlorinate. Okay, so that's one particular method that ends up being a review. There is another type of halogenation. It's a little more specific in what you can use it for, so not as general, and that's called allylic bromination. So what it's going to do is it will put a bromine, and there's no chlorination that's allylic, no chlorine equivalent. It's going to put a bromine in the allylic position to a double bond. So to give you an idea of what an allylic bromination would do, let's say we had something like this, and I had a double bond there. The allylic positions are the positions that are one removed from the double bond. So if we were to go and highlight those allylic positions, I've got one there, and I've got one there. And if I go and do an allylic bromination, I'll have my double bond, a bromine in that allylic position, and a bromine in the other allylic position. So what you do with that is you monobrominate, so it's a monobromination. You keep the double bond, so it doesn't go anywhere, and the bromine is in the allylic position only. So what we're going to do is, before we go and do some example problems of this and talk about some of the complications you could have, we're going to go through the mechanism, talk about the reagent that does that, and then we'll do a couple practice examples. So let's go ahead and let's talk about what would happen. There's a double bond. What would happen if I just treated this with Br2 and light? Remember that in halogenation of an alkane, it went through a radical mechanism. And this would ostensibly go through a radical mechanism as well. One sort of nice thing about that is if this worked and you would go a radical mechanism, the best place to have a radical, the most stable radical, would be in the allylic position. So if I could make a stable radical right here, it's stabilized by resonance. And to show you how that works, I could take that double bond and split it homolytically, bring that radical down, and I can draw a new structure where my double bond is now there and the radical is there. So you can see when you make an allylic radical, they're stabilized by resonance. That sort of explains why it prefers to go allylic. The problem with this is nothing to do with the radical, but the problem with this particular reaction is that bromine reacts very quickly with double bonds. So you wouldn't even get to where you had a radical. You would have a bromine add across the double bond like that. Clearly, that's not what we want. When we're doing an allylic bromination, we want the double bond to stay and a bromine to go allylic. That was not accomplished by this. So because bromine itself reacts with the double bond, we can't just use straight Br2 because it's not going to give us the product we want. We're going to have to do something different to get that radical in the allylic position. And so let's talk a little bit about the particular reagent that they use to avoid the problem that you would run into with Br2. And to avoid that, they use something called N-bromosuccinimide. There's a mouthful. So to avoid Br2 and that reaction with the double bond, we're going to use sort of a substitute, a different reagent that will give us bromine, and it is called N-bromosuccinimide. NBS for short. And it looks like this. It's a 5-membered ring with a nitrogen in the center. The nitrogen has a bromine on it, so there's your bromine, and it has double bond O's. So that is what N-bromosuccinimide is, and it is the source of the bromine radical, not Br2. N-bromosuccinimide won't react with the double bond. So we're going to run through the reaction of making the allylic radical and putting a bromine in the allylic position using NBS, and we'll show you how that actually works. Back and see if we can see it here. Right here, this top example, the Br2 was added in, and there was nothing but the double bond to react with, and so that's where it reacted. The difference now, though, all right, so you take NBS. This is the mechanism. Take NBS, and we're going to shine light on it. So there's my double bond O, Br, and you do light or heat. And we're going to generate a radical. What's going to happen is the nitrogen-bromine bond will cleave homolytically. And I'll get two radicals. One is the nitrogen radical, and the other one is bromine radical. That's my initiation step. Then that bromine radical is going to go and start the propagation. It's going to actually react with the alkane, or the alkene rather, and the reaction will start. So let's go into the propagation steps. We have our alkene, and there is a hydrogen, two hydrogens actually, allylic. And the bromine radical is going to react with one of the allylic hydrogens, and it's going to cleave that bond homolytically as well. And then the bromine will react. And I will end up with my double bond still there, nothing happened to it. I have a hydrogen on there. The other hydrogen's gone, but it left behind a radical. And then I have H bonded to Br. Now this radical is pretty stable. It's a stabilized radical. It's called an allylic radical. And as we showed earlier, you can stabilize it by resonance. So putting your radical allylic, if you can, is a really good choice because you can draw resonance structures and sort of spread that radical character around. So you have this allylic radical, and then in the next step, we are going to take another molecule of NBS, and it's going to react with HBr that we just generated. So that's HBr from above. And I'm going to make this thing called succinimide, so the nitrogen will have a hydrogen on it. And Br2. There's the Br2 that I talked about could potentially cause a problem with the double bond, right? But here's the difference. What's going to occur is this Br2 is now in the presence of this allylic radical, and it chooses to react with the radical. And let's draw the reaction out first, and then we'll talk about why that happens and not the double bond being attacked. So there's the radical, and I have my Br2, which is just Br. And what will happen is the radical will come in and form a bond with a bromine. So the Br breaks. One electron goes with one bromine, one goes with the other. When that occurs, there's my double bond. And here's my H. Now I have a new carbon-bromine bond. And I have a bromine radical, which then cycles back in through propagation step 1. So let's call this, for the steps, let's call that propagation 1, sort of propagation 2, and propagation 3. This Br radical will go back to propagation step 1 and continue the cycle again. Now, the net result is that I have accomplished an allylic bromination, and I haven't destroyed my double bond. I still have the double bond there. Now, as far as why that occurs, we talked about how Br2 was a problem with double bonds. This Br2 is generated during the reaction. I don't actually add it in initially. So for every radical I make, I get one Br2. So it's generated in very small amounts. And it's in the presence of a very reactive radical. So the Br2 really has two choices, places it could attack. It could attack the C double bond C, or it could attack the radical. The radical is much more reactive. And so as far as the choice of reacting sites, since the radical is so much more reactive, the C double bond C basically just gets ignored. That's the difference. In the earlier example, here is that I added Br2. I didn't add it, it was generated. So Br2 was added to the reaction, and it was added at the point where there was a radical. That was the preferred place for it to attack. Okay, so we're going to do a few examples, and we're going to see how there's a kind of a complication that can arise when you have more than one allylic position. You can start to get mixtures. Okay, so let's go ahead and do one example, and then we'll ratchet it up and do one that's slightly more difficult. So for our first example, we'll take an alkene and we'll treat it with NBS and light. And when you look in the books, you'll often see a solvent added, typically carbon tetrachloride. So that's just the solvent. The important part is the NBS and the light. Now, in order to figure out what the products are going to be, don't sit there and try to guess. What you want to do is first draw out your allylic radical. And if there's more than one, draw all of them out. Okay, so identify your allylic positions and then draw that radical before you draw a product. So looking at this one, I have one allylic position and it's right there with the red dot on it. And so what I'm going to do before I draw the products is I'm going to draw the radical right there. There's the radical. Now remember, this thing is resonance stabilized. So what I want to do next is draw that resonance structure. So we'll go ahead and we'll split this pi bond homolytically. One electron will go to the terminal carbon, and one electron will join up with the radical and form a new double bond. So there's my structure. My new double bond is right there on the internal part, and my radical's out at the end. So I have two allylic radicals here. One's my original one, and one is from the resonance. And you are going to get products from both. So for this particular example, I'm going to get two products. I'll have from my first original radical, I'll have the bromine right there, right where the radical is. And then from the resonance structure, I will have the bromine out at the end. So two different products. So it's very important that you, before you launch in and start drawing bromines everywhere, that you identify your initial radical or radicals, and then you start drawing all the resonance structures. That'll tell you exactly what the products are. So let's do one more example. Okay, let's go ahead and do a 5-membered ring. And we'll put an ethyl group on it and say a double bond right there. All right, so first identify all your allylic positions, every single one of them. So I have got one right there. I have a second one over here. And I have a third one right there. And let's make sure that there are no repeats here. Give me different things. Yeah, they should give me different things. Okay, so 3 allylic positions. So draw those 3 radicals first. So there's my ethyl group, there's my double bond. I'm just going to start at the top, probably guess I can go clockwise. So there's one radical right there. And the next one, here's my ethyl, there's the double bond. Second radical would be out there. And then the third one is the ethyl, double bond, and third radical is out there at the end. So that is identifying each allylic position. So these are all in red. These are the allylic positions. And I start by putting a radical at each one of those positions that I've identified. So there and there and there. Just put a radical there. Then, don't start guessing where your products are. Do the resonance structure for each of those. So I'm going to do the resonance structure for the first one, resonance structure for the second, resonance structure for the third. Drawing them out. Here's my ethyl. What I'm going to do for resonance is that electron goes up, that comes down. I just basically interchange where the double bond and the radical are. So the resonance structure for the first one puts the double bond at the top, radical right there. Resonance structure for the second one. Well, going and doing that. One electron comes in, the radical comes in, and one electron goes out there. So I will have the double bond into the ethyl group, radical right there, and the resonance structure for the third. Let's go ahead and split that double bond. One electron goes there, the radical goes there to form a new double bond, and the other electron is going to be right there. So I have a radical that's at the tertiary carbon, and double bond right there. Those are all my resonance structures. Everywhere you see a radical, draw a product. Okay, and then we're going to check to see if we have any repeats. Some of them may be the same thing, right? So I'm right now tentatively going to draw 6 products. We may end up eliminating some, or there might actually be 6 products. So let's go ahead and draw them out. 5-membered ring ethyl group. This is, I'm working on the top one. So right there. So double bond bromine at the top. Then the next one over to the right. Ethyl group, double bond there. Put the bromine on the ethyl group. Then tracking over to the last one in the top row. Bromine right there. Then I'm going to go to the bottom row. Double bond there, bromine there. The next one on the bottom row, double bond into the ethyl, bromine there. And then the last one in the bottom row, double bond there, bromine there. So everywhere with a radical, I stuck a bromine. So potentially 6 products. But let's see if we don't have some repeats. This one's unique. This one's certainly unique. That one's unique. And this one, the bromine is 2 away from the ethyl group. That one's unique. These first 2 that are in the column, these first 2, let's see, we have 1. If we call that carbon 1, carbon 2's got an ethyl, carbon 3's got a bromo. Right, so the double bond starts at carbon 1 and the bromine is at number 3. Do the same thing here. There's 1, there's 2, there's 3. The double bond starts at 1, bromine's at 3. These 2 actually end up being the same. And so I can say, I'm not going to consider that one. So net overall from this were 5 products. And we considered all the allylics and then all their resonance structures. 1 was a repeat, so we ended up with 5 products. So you guys have a homework where you're going to do basically just what we did here. You're going to draw all the possible monobrominated products for 2 molecules and approach it just like we did. Identify the allylic positions first and draw those radicals. Then draw the resonance form for each radical. And then where you have the radicals, that's where the bromine's going to end up going. So apply that same approach to each problem in your homework.